Hi, welcome to my presentation on Lab 3. In this lab, we use a circuit simulation to explore time-dependent graphs with RC circuits and current analysis. The procedure of this lab is split into two main parts. The first part is where we have a series circuit set up like this, and we want to measure the currents over the two resistors I1 and I2 using ammeters, a tool that is used to measure current, and we also will explore potential differences that ensure physics concepts such as the loop rule. And in the second part of the experiment, we are going to set up an RC circuit with a light bulb and to measure how fast the capacitor charges and discharges, and use these concepts to analyze time graphs to calculate RC values. The physics principles that we're going to use are the loop rule, which states that over a closed loop, the sum of the potential differences are going to equal 0. And in a series circuit as well, the total current is constant due to charge conservation. We're also going to go over Ohm's law, which is used for calculations of resistance and current across a resistor. And in an RC circuit, we are going to explore the time series graph with time and voltage potential differences. So looking at this above diagram, we can see that our loop rule is going to be, we can use the whole circuit as a loop. So we get 3 minus 47 times the first current due to Ohm's law, and minus 100 times the second current, also derived from Ohm's law. And because we know these resistors are in series, we can say that I1 equals I2, and we get a value of both of them equaling 0.0204 amps. And when we simulate this on the circuit simulator, we confirm this value as a 0.02 ammeter value is read from the ammeter, or amp value is read from the ammeter. Using a voltmeter that closes the circuit, we get a reading of -3 volts, which makes sense due to the loop rule, given that the EMF of the circuit is going to be 3, and to counteract it to make the whole closed loop 0, we would have a -3 voltage drop. Between the two resistors, we get using the voltmeter, we calculate a negative 0.96 voltage drop between the 47 ohm resistor and a negative 2.04 voltage drop over the 100 ohm resistor. This takes us to a 0 voltage difference over a closed loop. And calculating these three different resistance values, we get similar values with the original resistor with our 4700, and given that the ammeter reads 0, we can say that the resistance at the ammeter is also going to be 0 ohms because of the voltage potential difference also being 0. Moving on to the RC portion, we calculate with our 10 ohm bulb, it takes 5.2 seconds to charge and 5.6 seconds to discharge, and with our 20 ohm bulb, it takes 10.7 seconds to charge and 11.3 seconds to discharge. And finally, our analysis between time and potential differences, we get a very linear relationship using the 30 ohm bulb, and our slope of the line is -0.167, and we know with manipulation of our original equation up here that the slope is going to equal -1 over RC, so we get an RC value of 5.98802. And a calculated value of RC is going to be 30 times 0.2, because this is the resistance of the bulb and this is the Faraday value of the capacitor, and these are very similar. Source of error could be the lack of intermediate data points we used with our calculation, because we took larger time steps and different timing issues with the stopwatch in the simulation. If we're doing this experiment in real life, the real ammeter would have some resistance which would have affected the calculations of the current, because the resistance of the ammeter would have to be accounted for in the loop rule calculation. In the previous loop rule calculation, we just assumed that the resistance, or we knew the resistance of the ammeter was zero because the voltage, because the potential difference of the voltage was zero. And in real life, the capacitor would charge instantly due to a lack of resistance, but in reality, the wire would provide resistance in the circuit,